Greetings everyone, welcome to our YouTube channel. You are encouraged to subscribe so that you continue receiving notifications in any case of any videos that are posted on this channel. Today we're going to look at transformers in physics. So the first thing that we're going to do is to define what a transformer is. In our definition, we're going to say a transformer is an electrical device that is able to change the voltage of an alternating current supply. So we say an electrical device that is able to change. Changing means to transform, hence the reason why we call it a transformer. It's able to change or transform rather the voltage of an alternating current supply. So whenever we are talking about a transformer, we should remember that we are looking at a device that can either increase or decrease the voltage. So it can either increase or decrease an incoming voltage in an AC supply. So remember, AC means alternating current. It can increase the voltage, it can also decrease the voltage. Then we look at what we call mutual induction. For us to understand the transformer, we must also have an understanding of mutual induction. Mutual induction is the phenomenon in which a change in current, or the change of current in one coil causes an induced EMF. Now take note, EMF stands for electromotive force. So this electromotive force can also be called voltage in another coil. So we're going to go through this definition once again. We are saying mutual induction is the phenomenon, or the idea, you may say, the phenomenon or idea in which a change of current in one coil causes an induced electromotive force or an induced voltage in another coil, and these two coils must be right next to each other. So the first coil is considered as the primary coil, and the second coil is known as the secondary coil. So when we look at a simplified diagram of a transformer, we are going to see exactly how these two coils are related to each other. So we look at what we call the structure and operation of a transformer. You may be asked to describe how a transformer operates. So we're going to look at a simplified diagram of a transformer. So take note that this is a very simplified diagram. A transformer is made using soft iron. We're going to explain the reason why later. So this is soft iron, and then on one side we have a coil, which we can call the first coil or primary coil. Then on the other side, we also have another coil we can call the secondary. So we have primary on the left, and we have secondary on the right hand side. And these the two coils rather, are made around soft iron. So one may ask, why is soft iron used in making a transformer? So we can say soft iron is used because it is easy to magnetize. That's the reason why we use soft iron. Remember, an object that is easily magnetized is known as a ferromagnetic material. So iron is ferromagnetic. So this is exactly how a transformer is going to work. So we have a primary coil which is wrapped around the soft iron, or the soft iron core, and it's connected to an AC supply, so power supply in there. When the source is switched on, the current will pass through the coil. So the alternating current produces a magnetic field in the soft iron. So we're going to have a magnetic field there. As the current is passing through the primary, we're going to have a magnetic field that is going to be produced. So the alternating magnetic field, this is going to be an alternating magnetic field, is going to induce an alternating voltage in the output. It's going to induce an alternating voltage in the secondary. So we're going to summarize this. We say AC or alternating current in the primary induces an alternating magnetic field in the soft iron core. So that is the first thing you may be asked to describe. So these will be the things that you'll be required to expand in the description of the operation of a transformer. An alternating current or alternating voltage in the primary induces an alternating magnetic field in the soft iron. Now this alternating magnetic field further induces an alternating voltage in the secondary. Now this is the reason why we are calling it mutual induction. Mutual because an alternating voltage produces an alternating magnetic field. Then mutually, the magnetic field will also induce an alternating voltage. So we're going to have a voltage in the primary inducing magnetic field in the soft iron. Then the magnetic field in the soft iron induces what we call an alternating output voltage in the secondary. So we have two types of transformers. We have a step up and a step down transformer. Remember, initially we said the job of the transformer is to change the voltage. So when you're looking at a step-down transformer, just by the name itself, you should be able to tell that this is a type of transformer that is going to decrease the voltage. So a step-down transformer decreases voltage. So what we need to know in the step-down transformer is that the number of coils, remember we have a coil in the primary and a coil in the secondary. So number of coils in the primary, which we're going to denote as NP, is greater than coils in the secondary. And the coils in the secondary, this time we denote as NS. So NP for primary coils, or number of coils in the primary, and NS for number of coils in the secondary. So technically, in a step-down transformer, NP must be greater than NS. In some books, you may see NP being denoted as N1, which is number of coils in the primary, then N2 representing number of coils in the secondary. So in the same way, under a step-down transformer, the primary current, which is the current in the primary, we can call it IP, is greater than IS, which we are going to call the secondary current. These are the important conditions that we must take note of in a step-down transformer. Hence, in summary, in a step-down transformer, we have NP greater than NS. At the same time, IP is greater than IS. Remember, S stands for secondary. Then we look at a step-up transformer, which increases the voltage. So what do we know about a step-up transformer? In a step-up transformer, NP, which is number of coils in the primary, will be less than the number of coils in the secondary. At the same time, the current in the primary also will be less than the current in the secondary. So at this point, we already understand the denotations NP, NS, IP, as well as IS. We look at what we call equations for ideal transformer. But as we look at the equations, we must understand what an ideal transformer is. An ideal transformer does not really exist in reality, but ideally, this type of transformer is where there is no loss of energy. When a transformer does not lose any form of energy, it is considered to be an ideal transformer. In this case, it also means the efficiency of the transformer is equal to 100%. But we know that in machines, there is no such thing as efficiency of 100% because of external energies and external disturbances in the system that need to be overcome. So in this case, if we are looking at an ideal transformer, power in the primary coil must be equal to power in secondary. Now take note that this only applies when you're dealing with an ideal transformer. So this means in an ideal transformer, voltage in the primary multiplied by current in the primary, remember voltage times current is power, must be equal to voltage in the secondary multiplied by current in the secondary. This is a very important equation when you are dealing with an ideal transformer. Now take note that efficiency of a transformer is power output, which is V secondary multiplied by I secondary divided by V primary multiplied by I primary multiplied by 100%. So this is another formula that we must consider. This formula applies to any transformer, whether it is ideal or not. Now the first one only applies to an ideal transformer. When efficiency is 100%, that's the only time where power in the primary is equal to power in the secondary. Take note, there is another formula that we need to apply in our solutions. It says number of coils in the secondary divided by number of coils in the primary is equal to voltage in the secondary divided by voltage in the primary. So this is another formula that we must strongly remember, because when we're answering questions, it is the one that is applied. So we're going to look at a few examples. Here we have our first example. We are told that a transformer has 30 turns in the primary coil and 60 turns in the secondary coil. The input voltage is 100 volts. Is it a step up or a step down transformer? Calculate the output voltage, and if current in the secondary is 4 amps, find current in the primary if it is ideal. So what we're going to do is we're going to take down our data first. So you can pause the video, copy the question if you may. Then we're going to look at our provided information. We are told that number of coils in the primary are equal to 30, and number of coils in the secondary we have 60. When you go back to the statement, it says input voltage, which is V in primary. Okay, so V in primary is 100 volts. So Vp is equal to 100 volts. In question A, we are asked if it is a step up or step down transformer. So we can see clearly here that the number of coils in the primary are less. So we have number of coils in the primary being less than number of coils in the secondary. So definitely this is a step up. So this is a step up transformer. Question B. Question B says calculate the output voltage. So we're going to say number of coils in the primary, according to one of the formulas we wrote down, divided by number of coils in the secondary is voltage in the primary divided by voltage in the secondary. So we have 30 divided by 60 is equal to 100 volts divided by voltage in the output, which is voltage in the secondary. So when we do our cross multiplication, we're going to get Vs times 30 is equal to 60 rather, multiplied by 100 volts. We then divide both sides by by 30. This is going to give us our secondary voltage as 200 volts. Then the last question says if output current is 4 amps, find primary current if the machine or the transformer is actually ideal. So you can go back to the question and look at it once again. But we know that when we are dealing with an ideal transformer, VP times IP must be equal to VS times IS. So we are given the output current. As we go back to the question, the output current IS, which is I secondary, is 4 amps. Okay, so we already know that the primary voltage is 100 volts and we are looking for the primary current. The secondary voltage we found 200 volts. Then the secondary current given is 4 amps. Okay, then we can divide both sides by 100 volts. This gives us primary current as 8 amps. This is if our transformer is ideal. Our second example is about efficiency. You can pause the video and read the question carefully. So we are told that a transformer gave a reading of 15 volts and 3 amps in the primary. So we have VP 5 volts and IP to be 3 amps. Then in the secondary, which is VP, so remember VP rather should be 15, then VS, sorry. So VP is 15 volts, then VS, which is V secondary, should be 5 volts, and I secondary, which is current in the secondary, is 7.5 amps. So we are asked to calculate the power in the input. So power in the input is power in the primary, which is equals to VP IP, giving us 15 volts times 3 amps. That is going to give us 45 watts. Then the second question says power in the output, which is power in the secondary, giving us voltage in the secondary multiplied by current in the secondary. So this gave us 5 volts multiplied by 7.5. So we get 37.5 at 7.5 watts. Okay, so you can pause the video and do your own calculations and see if it matches what you understand. Then lastly, we are asked to calculate the efficiency, which is power output, power in the secondary. So take note, our power in the secondary was 37.5. So we say 37.5 watts divided by power in the primary, which is 45. Then we multiply by 100%. Okay, so this is going to give you an efficiency of 83.3%. We can now look at power transmission. Now take note that in Zambia we mostly use hydroelectricity. So how do we transmit this energy from its source to the rest of the country? Now remember that this electricity has to be transmitted over long distances, and this is done through electricity cables. But as this voltage is passing through these electricity cables, energy is lost. So take note that there is energy loss in transmission. The higher the electric current, the higher the energy loss, meaning more heat is generated, so more energy is lost. So we say the higher the current, the higher the energy loss. So how do we reduce this energy loss? So energy loss is decreased or managed. So we can say energy loss is reduced by reducing the current. Remember, we have already stated that the higher the current, the more energy is lost. So energy loss is reduced by reducing the current. Now take note that if we reduce the current, we have to increase the voltage. Okay? So voltage must be increased. That is the reason why electricity is transmitted at very, very high voltage. This is in the aim of reducing the energy loss. But how do we do that? We have already looked at transformers. So using step-up transformers. So the step-up transformers will increase the voltage from the source to where the electricity is needed. So this electricity is taken to a substation, and at the substation it has to be distributed into our households, and at this point the voltage must now be decreased. So we can say at the substation voltage is now decreased using a step down transformer. So this is how we can reduce the loss of energy during the transmission of our electricity. Now, how high energy transmission, remember we've said that this electricity is transmitted at high voltage. So this high voltage has its advantages. So high voltage transmission, but it also has disadvantages. So let's look at some of the advantages. Number one, energy loss is reduced. Number two, voltage drop is also reduced. So this is something that is of a ripple effect, meaning if you reduce the energy loss, of course even the voltage will not be lost, so you maintain a higher voltage level. Then because of this, cost is also reduced. So remember, if you let the energy be lost, even the output voltage eventually will be decreased. So to avoid that, we reduce the energy loss so that the voltage drop is also reduced. So if this transmission is not well managed, when not well managed, we have a lot of consequences. When not well managed, we are going to have scenarios of overheating, so it has to have constant attention. You also have low voltage, meaning that the voltage level is going to decrease. So you have low voltage output. And of course, you have increased damage to material. And look at damage to material. You are also looking at loss of efficiency. So that is low efficiency. That is if this transmission is not well managed. So something that you can include on your self-research, look at how energy is transmitted in your own country. So for example, in Zambia, we have underground and overhead power transmission. So carry out a research to find out advantages, disadvantages of each, and also their characteristics. So we've come to the end of our lesson. What you must do now is to look out for questions that apply to this topic and see if you're able to apply the knowledge. Remember that after subscribing to our channel, you will be able to receive notifications whenever a new lesson is uploaded. Thank you for your time.